Good day and welcome to this session where we will be talking about electrostatics. That will be our theme for the day, and as you would know by now, it's a grade 11 topic, so I hope that you, our learners that's currently in grade 11, can go through this topic, which will be accessible also in grade 12, and then our current grade 12 learners will be writing the final paper soon, that you will then be also ready should you sit down on Friday for the paper. So yes, these notes that I'm going to use will soon also be made available to our current grade 11s for future reference, and like I mentioned, it's a grade 11 topic. So without any further ado, let me start off with this topic, which is electrostatics for today. And like I said, you have done a little bit of this already in grade 10, and just for introduction to compare, electrostatics is the study of charges at rest. Now charges, when we talk about it, we've got two types of charges, which is electrons and protons, if we go to micro level. And yeah, it means that they are in rest, and that's the difference between electricity, where we have electric current, where the charges is moving. Yes, in electrostatics, charge can also move, like you will know when there is contact or friction. But apart from that, once an object is charged, it is all about charges at rest and the properties that then applies. So yes, let's have a look there. You know that what you've learned in grade 10 is that there is a force. That is what you've done in grade 10, that there's a force between charges. And also you will know by now that like charges, for example, negative will repel negative, and unlike charges like positive and negative will attract each other. And this charges, when they are at rest, there's a force between them, and that force is what we will then call our electrostatic force. So that is all that you've done in grade 10, and you've looked at those properties. And yes, now you will know when I talk about the force between charged objects, I'm talking about this electrostatic force because of charges repelling or attracting one another. All right. Now in grade 11 in the syllabus, which is also going on to grade 12, like I mentioned, you will learn more about the basic laws that apply. So we're going to build on the knowledge that you have already. The key concepts in this session that we are, and this is part one of two sessions, the key concepts is the type of charges and the electrostatics around that, which is mainly revision. Then we will look at the law of conservation of charge, and thirdly we will look at Coulomb's law, and then lastly we'll look at electrical field properties and electrical field strength. So that is the key concepts that you will find that we will address in this document. All right, now let us start off and start to look at the type of charges and the electrostatic forces that then apply because of those charges. You will know that we only have our two types of charges. The one is positive and the other one is negative. That is our two types of charges that applies. Now the next sentence is very, very important. This is key, that we define a positive charge or object that is positively charged as an object where electrons was lost. And a negative object that is negatively charged, we will say that that substance or that object, that we can also talk about an object, that those have gained electrons. So you will see the key word here is we define it in terms of loss of electrons or donation of electrons and gaining of electrons. We never refer to the protons, and the reason is very simple. If you think about the atom, inside the nucleus we have our protons and neutrons, which is fixed inside the nucleus. It's not free to move, it's not free to be donated or received by another atom. Around the nucleus we find our electrons, and through, like I mentioned, friction or through contact or through potential difference across it, electrons can move. They are free to move under certain circumstances, as mentioned. Right. So when an object is charged, we are going to measure that charge, and the unit that we use for measuring the charge is the coulomb. All right, and the abbreviation is a capital C. Now, the following you will find in your questions, they will sometimes refer to microcoulomb, nanocoulomb, or picocoulomb, and those are the N and the micro and the pico. They are abbreviations for this number. 10 to the power minus 6 is micro, and nano is 10 to the power minus 9, and pico will be 10 to the power minus 12. So you can see that the numbers that we are going to talk about will be very, very small. So if I can make an example, if I talk about 3 microcoulomb, then we will be using the number 3 times 10 to the power minus 6 coulomb. Now I have converted it to coulomb. If I talk about, let's say, 4,2 nanocoulomb, then it will be 4,2 times 10 to the power minus 9 coulomb. And you need to know how to convert the micro, the nano, and the pico. Those are the general ones we use with electrostatics, because you will see in electrostatics we work with very, very small numbers. All right, so and the same will apply for pico. I'm just not, due to time, I'm not going to do another example. I think you will understand what's happening here. All right, now we are looking at our smallest possible charge that can exist in nature, and all charges are multiples of this charge, and that is the charge of an electron. Now if you look at the charge of an electron, it was found that the charge of an electron is negative 1,6 times 10 to the power minus 19. So that is the charge of an electron, and all objects being charged will be multiples of that value. All right, and you will find that on your data sheet, when I go to the section that deals with electrostatics, that you will find that there is the charge of the electron given to you. So it's not a number that you need to memorize out of your head. It's given to you, that value for the electron, and the symbol that they have on your data sheet is E. And then of course you have also your formulas that you will be able to use should you be asked to do some calculations. Right, now you will find that in questions the abbreviation to talk about something that is charged or that have a charge, you will see that capital Q is the symbol that we will use, but sometimes you will then also find the small e when we refer to electron, or you will sometimes find a small q with a footnote e, which will also refer to the charge of an electron, or you will just find a small q. But that normally we do in diagrams, you will find them, but most of the time when we talk about the charge, and then it will be a certain number of coulomb that charge is, it will be a capital Q. Alright, so if the charge on an electron is then negative 1,6 times 10 to the power minus 19, then the charge of a proton will just be the opposite, because the proton is positive, the electron is negative. So you can see the only difference is this sign there, the positive and the negative sign. So this is also then given to you, but not direct on the data sheet. It is because you know that the positive is the proton. So this value is then also there for your use. Right, now let's start off and calculate how many electrons, in other words, what number of electrons an object has lost if it has a positive charge of 1 coulomb. I think just as referral, I like to always start off to know what kind of numbers are we talking about. So if an object is positively charged by a charge of 1 coulomb, and remember we said that the coulomb is the unit in which we measure charge, then we can now calculate how many electrons did this object lose, because now it will have more protons than electrons, and we can see what is that exact number. Now there is a formula on your data sheet that is given to you, and whereby you can calculate the number of electrons gained or the number of electrons lost, and in this case, because it's positively charged, we are referring to electrons that was lost by this object. So simple calculation, my charge was given as +1, and I know the charge of the electron, and when I take my calculator, and let us do this just now also for the purposes of exercise. Let's go through all the steps. You take your calculator and you switch it on, and you will go and you will say, all right, it's 1 divided by, and now it is negative 1,6. I'm not going to press the negative, although you can do it if you want to use your brackets. It's sometimes nice. Minus 1.6, and now to have the 10 to the power minus 19, I just press this button here. So I'm not going to press multiply, it's there on the button already, so there you will see it is, and then I can put in my minus 19, which is the value that must be added in there, close my brackets, equal, and there I have my answer, negative 6,25, 5 times 10 to the power 18. So that is the number of electrons. Now you have to, because this answer is in negative, and in this case I want to always motivate you to then make your assumption. So thus my 3 dots, thus 6,25 times 10 to the power 18 electrons was lost by that object. I hope you can see that when an object is charged 1 coulomb, it's a huge number of electrons that was actually lost. So we are either going to work with very, very small numbers, or in terms of electrons, it will be vast amounts of electrons that will be gained or lost when something is charged. And this now give you just an indication of the numbers that we are talking about. Now, of course, we can do the very same calculation for an object with a charge of negative 1 coulomb. So if we want to do the calculation to see the object is charged negative 1 coulomb, this means it gained electrons, then we will do the very same calculation. The only difference would be that there where I have my +1, it will now be my formula, which you always rewrite from your data sheet, will be equal to -1, which is now the charge of the object, and divided by minus 1,6 times 10 to the power minus 19, right? And then you will get the very same answer. The negative divided by the negative now becomes a positive, and I get 6,25 times 10 to the power 18, right? And now you will say thus 6,25 times 10 to the power 18 electrons. That's the number that I've calculated now. Electrons were gained. Right, so I knew, because the charge is just the opposite, that this value must be the same. That's why I could write down that because it's negative, it will be the same number gained. But there's your calculation that I've just shown you. All right, now this is very important that you know the following content, and that is that electrons is gained or lost through certain actions, and those actions will be friction or contact. That is how electrons move from one object to the other. Only electrons, we spoke about that earlier, can be transferred, and because of that transfer you will get an object being positively charged where it lost electrons, or negatively charged where it gained electrons. So you'll see this concept, I'm repeating it quite often just to make sure you've got this understanding that it's all about electrons, the gaining or the losing of electrons, donating of electrons. Right, so that is quite easy then, and you have that formula when it's all about the number that you can calculate the number of electrons. It's quite easy. Right, let us go on now and do a little exercise. Alright, so typical kind of question you can expect would be now the following. Let's do 1.1 together, An object has a charge of -6 nanocoulomb, and I know what the nano stands for. So, and I ask you now, calculate the number of electrons gained by this object. Alright, so you will say, okay, I see the following. I see that there is my question. First of all, I like to determine what exactly is the question. So I'm looking for the words directly after the word calculate. And I see it's a number. So I know that we use an N for the number. And then I see that the charge was given to me. I've got my charge. It was given to me. It's -6 times 10 to the power -9 coulomb. And now I want to know how many electrons have it gained. And I ask myself, what else do I have that they did not give me directly in this question? And then you will agree with me, I also have the charge of an electron. On my data sheet, -1,6 times 10 to the power -19 coulomb. My formula now, having these two quantities, would be, that will work perfectly, would be the formula that I get on my data sheet. Or it might be an E there, I'm not quite sure now. I think it's just an E, but it's fine. So now I substitute -6 times 10 to the power -9, and I substitute the -1,6 times 10 to the power -19, and the answer that we will get is the following. So I'm going to enter in -6 multiplied by 10 to the power -9, and I'm going to divide that by -1.6 to the power -19. Alright, and close the brackets, and I get an answer of 3,75 times 10 to the power 10. Let me just make sure. I think I had a small finger slip, so let us just do it again. -9 divided by, close the brackets, -1.6 multiplied -19, close it, equals, I'm correct, okay, 3,75 times 10 to the power 10. That's my answer. And now it's very good practice to say, thus this number of electrons, sorry, it's plus, were gained. And I knew it were gained because that charge was negative, so it had to gain electrons. So it's a huge number of, it's millions and millions and millions. Alright, so that was 1.1, and now let's go to 1.2. So now at 1.2, I'm telling you an object gained 1,5 times 10 to the power 6 electrons. So I'm giving you the number. So I'm looking here at 1.2. What was given to me was the number of electrons that an object gained. And from that number gained, I know that that charge will be negative because it gained electrons. Now I ask you, calculate the charge on the object. Alright, so I write down my formula, Q over the charge of an electron, and I substitute. My number will go in here under the number, which is now 1,5 times 10 to the power 6. I want to know what is the charge on that object, and here I'm going to give my -1,6 times 10 to the power -19, and now I have to calculate Q. So to be able to get Q, I'm going to go across with this number, so it will be 1,5 times 10 to the power 6 multiplied by that value, and that will give me my answer. So let's go for it. 1.5 multiplied by 10 to the power 6 multiplied by, let's use the brackets because there's a minus, -1,6 multiplied by, I shouldn't have put in a multiplication. Let's just delete that by pressing the delete button. Alright, There is now, to correct my times 10 to the power minus 19, close the brackets, equal. And I get an answer of negative 2,4 times 10 to the power minus 13. Alright, so that is the charge now, and I know I could check that my answer now is correct because I knew if the question said electrons were gained, I knew that this answer should be negative. So there is my answer, and now I still need my unit, which will now be coulomb. Alright, so same question, just from a different angle. I hope that exercise 1 is quite clear, and you will now be able to, and we will later on do more calculations as a little bit higher order questions we start to do that. Right, now we're going to look at the law of conservation of charge. There's a law that says that charge is conserved, and well, in basic terminology it means that charges cannot be created nor destroyed. Okay, it's conserved. It can be merely transferred from one object to a number. The total amount of charges in the closed system thus remains the same. So if I look at the total number of electrons and protons, that total number will never change. So if we look at an example, here I've got a duster and I've got a polythene piece of staff or a ruler or something, and before rubbing you will see I showed that for every positive there is a negative. You can count them, and here also. So you will find that both of them are neutral. The rubber is neutral, the polythene is neutral, so I've got two neutral objects here. And now, because of the action of friction, it is possible that electrons will now move from the one to the other. So when you look at this duster now, you will count more positives than negatives, and thus it means that the duster is now positive. Because of what? Because it lost electrons. The electrons were donated to the polythene ruler. So, and now if you look at the polythene, you will see all those electrons that it was lost by the duster is now on the ruler. So this is now negative. But to apply now my law of conservation of charge, you can clearly see that the total number of charges remain constant. So a charge can't split up into two small negatives or two pluses combined and be one big plus. It doesn't work that way. The charge is conserved. Alright, so I hope that is quite clear. Now let's look at the application on how we can do an application on this law. Okay, and we in our syllabus do it when we work with identical isolated spheres that has got a charge. That is all that is in our syllabus. This law applies under that agreement. All right, so we are allowing them to touch each other. It's almost the same action as friction. Electrons can then be transferred from the one body to the other. Okay, and the example I have here is two spheres A and B, two objects A and B, and I give you, they are identical, they are isolated, so charges can't be transferred or from other bodies except between the two of them. Right, and I give you the charge there. I show you that A is plus 5 nanocoulombs, so there it was given to you, and then I say, and B is negative 3. That is the charge on B. It's negative 3 nanocoulomb, and I said they are 0.1 meters apart. Right, and we know now, because they are oppositely charged, that they will attract one another. There will be a force of attraction between them. Alright, now if we go and draw the free body diagrams, which will now representing the electrostatic forces that acts on each object, it will look as follows. There will be a force to the right on A, because they are attracting one another, it will be towards one another, and there will be a force on B because of A, which will be to the left. So there's my free body diagrams. There will be a force, and we will later see the nature of this force, but I can tell you now that they will be equal in magnitude, but opposite direction, as you can see from the arrows. That is because of the attraction. But we will look more into detail on that later. Now, here is a formula which is not on the data sheet, and this one you have to memorize then. And that is now, if the two bodies is allowed to touch. Now we know that electrons is going to move from the more negative body to the less negative body. So because the one is negative, the other one is positive, we can know that electrons will move from the one to the other. And now the two bodies will have a new charge. They will have a new charge because of that movement of electrons. Now here is my formula that I can use to calculate that new charge which will be on the two bodies. Now there's a couple of things that you then can realize, but let's first do the calculation. So it's I just take the two charges, add them together, and I divide it by 2. So if we look at this one, it's 5, and I think it's minus 9 because it was nanocoulomb. And now I'm going to plus, and I'm going to plus the negative 3. So I use my bracket again, negative 3 minus 9, close the bracket, and that I'm going to divide by 2 equal. And I get an answer of, looks like I made a little mistake here. Could it be? Let us just go back again. I just want to do this one again. I got 1 the first time. I just want to make sure where is my mistake. Alright, let's go again. 5 minus 9, that is the 1, and I'm going to add to it plus, and I'm going to add negative 3 minus 9, close. Let's say equal. Okay, there I've got now the value at the top, and that value I'm going to divide by 2. And let's be careful. Now I'm happy. I get my answer that I got previously. I think I made a mistake there somewhere with my algebra. Right, so that will be the charge now, the new charge. That's what I get. Now here's a couple of things that is quite important, and that is if two different charges is allowed to touch, after that touch they're going to have the same charge. They're going to have a new charge, and the charge on both of them will be the same. That is very, very important that you realize this situation. And now the A and B will have similar charges, and because they have similar charges, now that we know they're going to repel one another. Alright, and electrostatic forces, where it was previously towards one another, will now be away from one another. Okay, and later on we will do a question where we will check what happened also to the magnitude. We are just saying that the direction is now away. Switch around. Why? Because now they repel. Sorry for that. Repel one another because they repel each other. So let's say these two are positive, then the forces would also have been sorry for that, I have to say excuse me. Then it would also have been to the left and to the right, and then afterwards it would still be repelling one another because it's going to be the same. And the same if both were negative, but negative, positive, they attract, but after touching you can know two things. They will always have the same charge, and it will always be repelling one another after touching. That is a given. You can know that is correct. Okay, and a question that you can expect to get in the exam, and I'm going to deal with this here now, is that we like to ask this. Let's say that I give you the following. I tell you that charge Q and charge, let's call it small q, that this one is 10 nanocoulomb and it experiences a force of repulsion of F. If this one is 5 nanocoulomb, what will be the force of repulsion that it's going to experience? Now, like I said here, before touching one another, those two forces will be equal in magnitude. It might be attraction, because if they were positive negative, in this case it's positive positive, that's why it's repulsion. But the mistake learners make is they think that because this one is less charged, that it will not experience the same force. In magnitude, the same force, okay, and opposite directions. Okay, now I let them touch. I let them touch, and if I let them touch, new charges is going to be on them. On this one, you will see it's going to be 7.5 nanocoulomb. On this one now, it's going to be 7.5 nanocoulomb. That's the first thing that we realized, is that the charge on them will now always after touching, it will be the same. So you can see the difference. This is after touching, okay, and the other thing that you can know that will always happen is that these forces will be repelling one another. There will be forces of repulsion, and also this force will not necessarily be the same magnitude as that one, but these two will have the same magnitude. So there it will be same magnitude, here it will be same magnitude. That one, don't fall into that trap. All right, even though they might be differently charged, the force is of the same magnitude. Here you can know the charge will be of the same magnitude and the force will be of the same magnitude, but always repulsion. I hope I made that very, very clear. All right, now again, let us look at just an exercise or two. All right, so you will see that what we have done here is we've done two calculation type questions now. The first one was where electrons was transferred and we could count or calculate the number of electrons, and then also the second one was now where we can calculate if they touch, what will be the new charge on them. All right, so that is what we've done so far in terms of calculations using the law of conservation of charges. Now let's look at exercise 2, the first question there. Right, the first question states, using the above example. Right, so what is the above example? It is where I have those values. Okay, using that example, where using the and the side, I assume that there's a word missing there. Explain whether A gained or lost electrons after contact with B, and then also calculate the number of electrons gained or lost by A. So let us first look at A. A is positive, B is negative, and because B is more negative than A, then B would donate electrons to A. So I hope you will be happy that I can say A will gain electrons. A will gain electrons. That is a given. Now, the second part, calculate the number of electrons gained or lost by A. Okay, so we know that on A, before touching, the charge on A was equal to 5 nanocoulombs. That was given there. And we have now calculated that the charge on A after touching, will the charge on A be equal to what did we get? 1 nanocoulomb. All right, so I'm going to do this and find two ways, and then you can choose which one will work the best for you. Okay, so that is my situation. I want to know how many electrons, the number of electrons. Calculate the number of electrons gained or lost by A. Now we know we gained. All right, so let us see initially how many electrons did A have less than protons. So I'm going to calculate the number of electrons that it lost, or the difference between protons and electrons. So it will be Q over E, alright, and that is equal to 5 times 10 to the power minus 9, because it's nano, divided by minus 1,6 times 10 to the power minus 19, and I have to do this on my calculator, and you can quickly there by yourself check if you agree with me. So let's just clear it. It will be 5 times, no, not times, I'm not going to do that, I use my time there, minus 9 divided by negative 1.6 multiplied by 10 to the power minus 19, close the brackets, okay, and I get my equal to, and my answer is equal to minus 3,125 times 10 to the power 10, and that's the number of electrons that it initially had protons more than electrons. Now look at the situation now, so that is initially. Now after, let's call this final, okay, it is the same formula divided by E, and now it's 1 nanocoulomb, 1 times 10 to the power minus 9 divided by minus 1,6 times 10 to the power minus 19, okay, minus there, and this is going to give me the following answer. So I've got 1 minus 9, that is the one at the top, divided by minus 1.6 minus 19, right, and answer is, let's just put it into, I don't know what I'm doing wrong here, let me just check again. 1 minus 9 divided by minus 1.6 minus 19 equals, it should give me the, I think it's just not set to give me the scientific notation, but I can do that quickly myself. Gives me negative 6,25, and now I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the power 9. Okay, so I've got the two amounts of electrons that it had. So you can see that this number is more than that number. No, that one is more than this one. Okay, so now to get the number of electrons that it received, because that was the question. The change in the number of electrons thus was my final electrons, my final number, minus my initial number. Now I'm seeing what is the difference in electrons now. So I will get that initially it had 3,125 times 10 to the power 10 electrons. No, sorry, 10 electrons more than the protons, minus 6,25 times 10 to the power 9, and I will get an answer of, let us do this one quickly on the calculator, 3.125 to the power 10 minus 6.25 to the power 9 equals, and I get an answer of 2,5 times 10, which is 25 electrons. So it gained 25 electrons from the other body. It was positive, now it's less positive. And there's my answer, 2.5, oh sorry, it's 2.5 times 10 to the power 10. I thought it looks like too little number. Okay, that's equal to 2.5 times 10 to the power 10 electrons that it has gained. Remember that negative, I will actually say thus 3.125 blah blah blah, and that one I will say thus 6.25. So it's to get the number, I will then just know that that is the amount of electrons it had less than protons. So I will just show what is the number by taking the negative away, and we did that earlier. Okay, so final minus initial. Now there's another way. Let's do that. Let's do it in a second way and see if we get the same answer. I've got my before charge and I've got my after charge. So my difference in charge would be the charge after minus the charge initial. So let's see if we get the same answer. So I get the after one was 1 nanocoulomb minus, and the before or the initial is 5 nanocoulomb. Now you can press your calculator. I will get minus 4 nanocoulomb. That is the change in the charge. Okay, and now I go and I work out my number is the change in charge over the charge of electron, and let's see what we get. We get minus 4 times 10 to the power minus 9, and here we get 1.6 negative times 10 to the power minus 19, and this will give me the following. Let's see. Now there's my calculator and clear it. Negative 4 times 10 to the power minus 9 divided by negative 1.6 times 10 to the power minus 19 equals, and you will see we get exactly the same number, the same answer. There's two ways of doing this calculation. That is the number of electrons that it has gained, right? Because now it's less positive. Okay, so there's your two ways. You either calculate the change in the charge, or another way that you will find a lot of learners like to do is they calculate what was the deficit of electrons, what is the deficit of electrons now, and then you get the difference between the two, and it will show you how many electrons that it gained. Okay, so I hope that the two ways of doing it is now quite clear. Right, now if we go to 2.2, I say here a sphere X had a charge of 3.5 microcoulomb before it came in contact with sphere Y. After contact, Y has a charge of minus 7.8 microcoulomb. And then I ask you, calculate the charge on Y before contact. Okay, so there's a couple of things here that if you understand it, this question is quite easy. So I have a sphere X, and I know what was the initial charge on it. The charge on this one was 3.5 microcoulomb. Alright, and now after it touched, then what did they give me there? After it touched a sphere Y, after contact, now I know Y has got a charge of negative 7.8 microcoulomb. Alright, now the first thing, I know that after objects touched, and we will talk here about identical objects, isolated and so forth. Alright, so after they've touched, that sphere X also will have the same charge. That's what we did earlier. Earlier there it is above you. you can see there we said the charge on them after touching will be the same. So if they only give me the charge on Y, I actually also know what is the charge on X. Okay, and now they ask you, calculate the charge on Y before contact. So I'm looking for that charge there before they contact it. Alright, so now we're talking about contact. So the new charge, which is the same for both of them, will be equal onto the before charge of Y plus the before charge of X. Alright, and that will be divided by 2. So we got this new value, that one, after these two with their initial values have touched. Now, so I can say, okay, this is fine. So in the place here, I'm going to enter minus 7,8 times 10 to the power minus 9, which is that value there, equals, and I don't, that is my question, what was the charge on Y, plus they've given me the before charge on X. Okay, so that will be 3,5 times 10 to the power minus 6. Sorry, I said minus 9, it's micro, it's minus 6. Sorry for that. Minus 6 is micro, and that was divided by 2. Right, so now I can see I'm going to multiply across to get rid of the 2. So let's do this. Okay, we've got negative 7.8 times 10 to the power minus 6, and that I'm going to multiply by 2 equals. Alright, so now I've done the part of the 2. Okay, so now I want to take the plus 3,5 also over to that side, so I will change that sign. So it will be minus 3.5 multiplied by 10 to the power minus 6 equals, and there is my answer. Qy is equal to negative 1.91 times 10 to the power minus 5. Okay, and it will be Coulomb. So you can see in this case, I've given you the new charge, I've given you the charge of X, and the question was calculate the charge on Y. Okay, so I hope you can see now different applications of this very same situation. Right, so this is our first hour that is concluded now. A lot of the basics. When we come back now, then we will start to work on Coulomb's law, and we will also go towards the last part, because you will see here we've done the first two key concepts already. So now it's Coulomb's law of electrostatics, and then also electrical fields and the properties and the strength of electrical fields. Right, so I'll see you for the next session, where we will go into much more serious calculations now. And if you can do those, you will do well in this question. I hope so far it's quite clear.